All right, so we finished the big process dynamics piece of the course. However, there's still one important topic left to really cover before we can dive headfirst into controls, and that is the idea of transfer function. um, we won't see in this video, however, we will in this series, that transfer functions lead to kind of control schemes, control block diagrams that we can then use to fully describe and further control the process. So in this video, we're going to talk about how we can implement kind of our process dynamics understanding into a transfer function. And then in the next videos, we're going to relate that to control transfer functions and then put it all together to develop a control scheme. So right here, let's start with our process again. We're going to start with our tank process that is in the very first video of this course. And so what we're going to do is start with the differential equation that we had derived in the very first video, relating the height to the volumetric flow rate as an input. And what that looked like was as follows. We said cross-sectional area times change in height with respect to time is going to be equal to volumetric flow rate in minus area of the whole square root 2g h to the 1/2 power. And what we did originally was numerically solve this equation using our simulation software. And then we kind of used that as our answer is what's going to happen in the system if we make a step input change to our input variable here, which is our volumetric flow rate in, right? So what we're basically going to do is derive the same understanding here, except we're going to come to an analytical solution as to how changing our input variable q will affect our output variable h. And again, now that we're in kind of the control portion of the course, it's really nice to think of things in terms of input and output variables. So the first thing that we're going to do with this equation is notice that we actually have it in a nonlinear form. That h to the 1/2 power there is nonlinear. And so what we should start to think about is, okay, what are some ways we can linearize this equation? And the first one that'll pop into our head is a Taylor series expansion, right? And so how do we actually perform a Taylor series expansion, right? We take, the derivative and then multiply it by our term and factor that out, right? So let's go ahead and do this for this system here. Our Taylor series expansion should look exactly like this, right? So we can say AC dH dt equals U in, that's not going to change, minus AH square root 2g, right? And now we kind of get into our expansion of this h to the 1/2 term. So what are we going to do first? We're going to just do the square root of h bar, and then add to that the derivative term, right? So then that would be derivative of h to the 1/2 is going to be 1/2 h to the negative 1/2. And we'll talk about this bar notation here in a second. And then we want to do the difference here. So it would look like that. Okay, so what have we really done here, right? Remember, this is our f prime term for our function, and then this is our h minus h naught. So our bar terms here are going to correspond to our steady state variable, and the non-bar terms are going to correspond to our non-steady state variable, right? So at this point, it kind of behooves us to define a term called deviation variables. And what this really is anything that's going to change, right, as a function of time in the system. So in this system, it's really easy. Our input flow rate and our height term are going to change. Meanwhile, our cross-sectional area of the whole, gravitational constant will all remain constant. So the idea of developing a transfer function is, in its most basic form, attempting to simply connect deviation variables. How does one variable um, change affect the response of another variable? And in this case, we're going to basically use the steady state variables in each of these cases to denote kind of a zero term so that our axes are kind of normalized to some sort of extent. And so that's exactly what we're going to do. We can go ahead and actually define Q next, Q in. We're going to just call this Q now from now on. And this should really be Q. Q prime would be Q minus Q bar. And so our prime terms then are going to correspond to the deviation variable itself. The bar term will correspond to steady state, and then our, I guess just our regular term will go ahead and correspond to what the system is experiencing at any given time, right? Okay, so let's see here. What do we want to do next? So let's go ahead and attempt to kind of define what our system looks like at steady state here. So at steady state, obviously our change in height is going to be 0. And so then what will that do to our system? Well, actually, I don't think this should be bar at all. That should just be H, right? Okay, yeah. Remember, we messed up our Taylor series expansion. So this should be f of x. This should be f prime of x. There we go. Yeah, there we go. That looks right. So now when we come back to at steady state here, what we want to look at is, well, our change in height is going to be 0, which is our volumetric flow rate minus area of the whole square root 2g times square root h here. And so then I guess because of course this term is going to go to 0 in steady state, right? Because what we really have here is that deviation h minus h bar gives us a change from steady state, and there would obviously be no change from steady state if we're at steady state, right? So h minus h bar would be 0, which means that f prime of x term is being multiplied by a 0. That entire thing can go to 0. Okay, so let's kind of move on now. We've gone ahead and defined what we look like at steady state. And so we can then plug this back into our equation for dH dt above. So we can say area of the cross section times dH dt then is going to be what? It's going to be, this should really be d8. let's talk about what if we make our h in our derivative term deviation, what would that be? So this would be q then minus q bar minus, right, we'd have area of the whole square root 2g square root h minus h bar, right? And so times our second derivative term here. And so that's just done by, again, I guess at steady state, we're denoting these as bar terms, right? So all of that is just simply subtracting off our steady state from our original equation here, right? Where that 0 is dh bar dt, right? And so that's exactly what we've done. We've subtracted that 0, but now quantified that 0 in terms of the right-hand side in this line. So that's what we did there. And so now what we've kind of found ourselves is our differential equation in terms of deviation variables. And so this is kind of an important step. And it's been linearized as well. So now that we've done that, let's go ahead and see exactly what would happen if we go ahead and try to solve this. So the way to solve this is to use our Laplace transforms. And we actually have a table of them provided. I'm not going to pull that up right now just because the ones we're going to use are easy enough that we have them memorized. So, for example, L of regular H is going to turn into capital H. L of, let's see, L of dH prime over dt is going to give us sh, right? And kind of the only other, I think those are just really the only two we need here, just translating out h for q at some points. So let's go ahead and write this differential equation in the Laplace domain, knowing these functions. So remember, Laplace is a linear operator, which means any constant multiplied by something. We can also bring that out in front of the Laplace operator, so it won't be changed. And with that, I think I've given enough background on Laplace that we can just go ahead and plug this in here. So that gives us area of the cross section times SH equals, we're going to have big Q now, right? Laplace of a deviation variable is going to be big of that variable, minus this all at this point. I'm going to go ahead and consolidate this into a term we're going to call alpha, just so I don't have to keep writing out that same constant. So alpha over 2 square root h bar, right? That should have a bar over it. And then multiply by root h minus h bar, right? Awesome. Now, that we've done all this, what we need to do is, oh shoot, messed this up. H minus h bar, this is going to be big H, right? And we've gone ahead and, yeah, so this should just be big H. And so now we're in the Laplace domain. We're going to go ahead and basically algebraically manipulate this equation to solve for h. So AC SH plus alpha 2 root h bar times h equals q. So factor out the h. And then divide across. So we're going to say h then is what? 1 over AC S plus alpha 2 square root h bar times q. And now we've kind of got our transfer function right here. So what is this transfer function doing? It's giving us completely in the Laplace domain. It's saying how can we manipulate q to give h. So the next thing that I'm going to go ahead and do is using a bit of kind of background knowledge on the system. I know that, or we know rather, that this is a first order transfer function. And I'm going to go ahead and prove that. So a first order transfer function is a function that has the form, whatever your output is going to be k tau s plus 1 times whatever your input variable is. Obviously, our output in this case is q. Sorry, output should be h, input should be q. So how can we manipulate our transfer function to give this form here? Well, what I would do is we're trying to make this term right here 1. So let's just go ahead and factor that out of the bottom, and then kind of pull that out and put it on top to give our k. So if we factor that out of the bottom, what's going to happen is our denominator will look like AC over alpha times 2 square root h bar, right, plus 1. And then we factored it out of here. So now we have alpha over 2 root h bar, right? And then we're going to flip that to put it on top. So 2 root h bar over alpha. And that is our transfer function. Except now it's in a first order form. Right? Neat. Okay. So what was the purpose of doing that? The purpose of doing that is that there's actually a Laplace transform that's really easy to manipulate kind of from this path. And that Laplace transform is the Laplace transform of, let's see, it would be k over tau s plus 1 is equal to, it should be a k 1 minus e tau over t. No, t over tau, I think. Looks better. T over tau. And maybe I should double check that. That looks right. And so from that, and of course our A, what is A here? A is going to be related to our input variable here, right? Yeah. I guess I could put Q. This will be Q minus Q bar. Yeah, that looks right. So from that, then, go ahead and kind of siphon this out. So let's go ahead and pull it out. Say we're in deviation variables, so h prime is going to be equal to q minus q bar times k. Our k is 2 square root h bar over alpha times 1 minus e t, because we're now in the time domain again, over tau. What is tau? Tau is basically k times a c. So k times ac. And again, our k value is 2 square root h bar over alpha. Awesome. If we want to find our actual height in terms of not just how it's being displaced from its steady state value, but what it actually is, we could say it's h bar plus this whole equation right here. Okay, so that is our analytical solution here. Analytical solution. Let's see. So that's it. And the only other thing left to do is to go ahead and simulate this. So let's kind of compare how our numerical solution here compares to our analytical solution that we just found using kind of control theory here. Let's jump on over to Colab. Hopefully you find it there. Throw in our input. We got subplot import subplots, and from sci-fi dot integrate import solve IBP. And the reason that we're doing that, again, this is for our numerical. Okay, our imports are in. And what are we going to do here? So problem statement 2 actually gives us a couple givens. It says that we have a cross-sectional area of 2, that we have a drainage flow of 0.5 H minus, well, it says we have a drainage flow of 0.5 H minus square root meters cubed per second. Not exactly sure what that's trying to say. I know that we have a Q steady state of 0.5 meters cubed per second, and that we have a new Q of 0.55 meters cubed per second. I guess it's saying the area of the hole is 0.5, and that we can go ahead and say that then alpha is going to be equal to 0.5 times NV dot square root 2 times 9.21, which is our G. Okay. So now what we need to do is go ahead and solve for our height. at steady state condition, right? And what that is going to be is, of course, our height at steady state should just be, what should it be? It should be the area should be U steady state. Let's go back here for a second and just write it out real quick. Height at steady state is going to be, we know Q equals area of the whole root 2g, which we're calling alpha here, times h to the 1/2 power. So it should be Q over alpha squared. So Q over alpha, I can spell, squared. Okay. So then, I think that's all the inputs that we will need, right? So let's go ahead and do it numerically first. This is exactly what we did in the very first video of this series. Basically, all we're going to do is define our right-hand side of the equation, and input T and Q. And Q is obviously our input volumetric flow rate. And all we're going to do is return height is going to be what? It's going to be, what's the right-hand side of this equation? It should just be Q minus alpha times h to the 1/2 power. And our input should actually be h, not Q. Bring me up there. Not h steady state, but h. Okay. Res should be solve IVP, right-hand side, time span. Let's go ahead and define a time span as a lens space here. Actually, just start with the end. Let's say 50. The time span, we can say from 0 to 10. Initial condition here should just be h steady state. And then method is going to be so last instance equal to true. Put some brackets here. Awesome. So then res y, I believe, gives us our height. Sol.res res.full. Okay, so that's our y values then. And what do we want to do with this? We want to go ahead and plot it up. So big equals make subplots. Big dot up layout. Width 600, height equals 400. template wave dark. And what do we want to add as a scatter? We want to go ahead and say x should be t plot, y should be y, and mode should be lines, and name can be numerical. So then let's go ahead and define t plot here as a twin space from 0 to t end. That's a good point. Okay, I knew I had this wrong. Let's actually make this res.soul over plot. I'm gonna have to find that obviously after this. That's right. No, still. This is likely due to there being an extra array here. Let's see if it works. Oh, perfect. Okay, so maybe I ran it a little bit long. There we go. Okay, so there's our numerical solution. And now we just want to go ahead and add our analytical solution here. So again, our analytical solution is just what? Basically, we want to solve this equation that we came up with for every single time piece. So how can we go ahead and do that? Go ahead and define right-hand side analytical, put in t, put in, just put in t, and then we're going to go ahead and return h steady state plus q minus q steady state times 2 times maybe that's square root h state divided by alpha multiplied by 1 minus exponential t divided by again our k, which is 2 times square root h steady state divided by alpha and that should be. Then what we want to go ahead and do is basically solve this for every single time. So that will be y plot 2 is going to be right hand side a or t plot. Oh, didn't run this. And then we're just going to go ahead and add here. Big dot add scatter x equals plot y equals y plot 2 mode again be lines and our name should be analytical. Going down the wrong side there. This should plus. No, definitely not. Should time be in the bottom of this? Okay, maybe not. Um, oh, our T is, it should be decaying over time. There we go. Okay, so as we can see here from this plot, our numerical and our analytical are quite close. In fact, it looks like what? Looks like the fourth decimal place, or the fourth decimal place is where they start to differ. And so we can see their transfer function appears to be a pretty good solution of the system. Obviously, if we had some experimental data, it would be kind of interesting to compare which one is actually closer. Although, obviously, the way that we could improve accuracy on our analytical solution would be to add more terms to our Taylor series expansion. All right, so that's all for this video. And the next one, we'll take this idea a little bit further in applying it to finding a transfer function for slightly more complex systems. See you then. Bye.